So I am going to go over homework 6. So in problem 1, we have to graph some functions, find where they're increasing, decreasing, relative maxima, relative minima, where are they concave up, where are they concave down, and so forth. So let's start with problem 1B. So we have the following cubic curve given by the function x goes to 2 times x cubed plus 7 times x squared minus x minus 4. Oops. Minus x minus 4. And it's always good to know what a curve looks like. So let's just plot f of x. And it's not too clear what's going on in this region. Let's just maybe plot it from x going from -6 to 6. Aha. So it goes up, down, up. Maybe better if we do it from -6 to 4. Yeah, that's pretty good. So you can see before you start roughly what the answer is. Here it's increasing. Here's a relative maximum. It's decreasing. Somewhere around here is a relative minimum. Then it's increasing again. Here is concave down. Here it's concave up. So somewhere around there is an inflection point. So that's what we have to find. So so let's just make a little note. So f of x is increasing when the derivative of f of x is positive. And the derivative f of x is decreasing when the derivative of f is negative. So what's the derivative of f of x is just this quadratic. And suppose we want to find when is this derivative positive. So when is the derivative of f of x greater than 0? Aha. So we're solving an inequality, and it's positive in this interval and in this interval. If we want this as, let's see if this works. Let's see if we want to get this as a decimal. Yeah. So from -infinity to -2.4, it's increasing. And from 0.069, it's increasing. And if we want to know where this function is decreasing, it's on this interval. So let me just make a comment. F of x is increasing on the 2 above intervals, these 2 intervals. And f of x is decreasing on the 1 above interval. So already we can tell where there's a relative minimum and when there's a relative maximum, because it's where the curve changes from increasing to decreasing is a relative max, decreasing to increasing. Or we're going to have Maple find those points exactly. So we want to know when is the derivative equal to 0. And it's at these 2 points. So these are the critical points. I could give them a name. I could say, let's say, CP stands for critical point. And let me just use F-solve because that gives them to me as decimals right away. So the 2 points, and CP1 is the first, CP square brackets 2 is the second, and we can use the second derivative test to determine relative maxima and minima. And the way we do that is just evaluate the second derivative. How do we get the second derivative? D at 2 of f of x. Oops, it's supposed to be a parenthesis there. And not a 9. Yeah, I mean, this is the function. That's the first derivative. Differentiate this, you get 12x plus 14. So if we evaluate the second derivative at the first critical point, it's a negative number. So by the second derivative test, CP1, which is minus 2.4, is a relative maximum. And if I evaluate the second derivative at the second critical point, it's positive. So the second critical point, which is 0.069, is a relative minimum. So that's so we found the intervals where the curve is increasing and decreasing, and where and the relative max and min. What about concave up and concave down? So we know that the function f of x is concave up, where the second derivative is greater than 0, and concave down, where the second derivative is less than 0. So let's solve the inequality. Second derivative greater than 0, minus 7/6 to infinity. So f of x is concave up on the above interval. Let's look at the graph of the function. Minus 7.6 to infinity. That's about here to infinity. It's concave up. Where is the second derivative? Negative. Minus infinity to minus 7.6. So it's concave down on this interval. And so it clearly has an inflection point at x equal minus 7.6, because that's where the concavity changes from down to up. And if we want to just double check, where is the second derivative equal to 0? Minus 7.6. So f of x has an inflection point at x equals minus 7.6. I just say at the above point. I'll do one more. See what it looks like. Let me do G. No, I'll do G. Oh, that's interesting. This is problem 1, G. And in this problem, we're looking at the function f, which is a trigonometric polynomial. It's equal to 2 times the sine of x plus the cosine of 2 times x. And we're interested in this function only for x going from 0 to 2 pi. That's interesting. That's what it looks like. When you look at this guy, it looks like it has a relative maximum here and here, a relative minimum here and here, and so forth. So let's just repeat our analysis. First of all, the function is increasing, where the derivative, where the derivative of f at x is positive, but we're only interested in x from 0 to pi. Oops. Why doesn't this want to work? So the inequality solver doesn't like a restriction on x. So let me just solve this inequality for x. And we get a lot of intervals. So I guess we just have to find the ones that are between 0 and pi and 2 pi. So here, 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 that's it. So we can say that f of x in this interval from 0 to 2 pi is increasing for x in the intervals zero. So Maple doesn't want me to write pi over 6. It wants to make this whole thing a fraction. Well, let's try that. Pi over 6. See if I can copy and paste. Pi over 2 to 5 pi over 6. And up to 2 pi. Because we're only looking at the interval from 0 to 2 pi. So here it's increasing. Here it's increasing. Here it's increasing. There are 3 intervals, and that's what we found. All right. Where is the function decreasing? Where the derivative is negative. And we get a lot of intervals, but the only ones we're interested in are the intervals between 0 and 2 pi. So this is this, these two. Yeah. And again, there are 2 intervals where the function is decreasing, here and here. So we can tell increasing, decreasing. Here there's a relative max, here there's a relative max. So we could just say there's a relative max at pi over 6 and a relative max at 5 pi over 6. But just to double check, suppose we want to solve where is the derivative of f of x equal to 0 for x going from 0 to 2 times pi. Huh, it just doesn't like that. I don't know why. Solve x equals 0. So again, it gives us several zeros of the function, but of the derivative, but we only want the ones between 0 and 2 pi, and those are pi over 6, pi over 2, 5 pi over 6, and it's not giving us this one. It's only giving us the zeros between minus pi and pi. I don't know why it doesn't want to give me all the zeros. So in any case, so we have pi over 2, pi over 6, 5 pi over 6, but we can also tell, because here it's decreasing and here it's increasing, that oops, what happened to this? So increasing, 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 goes up, turns around at pi over 6, turns around at pi over 2 and is increasing again till it gets to 5 pi over 6, turns around and is starting to come down till it gets to 3 pi over 2, increasing till it gets to 2 pi. So max, min, and I don't know why it doesn't want to solve this way I would like, but well, let's just double check the second derivatives. That's the second derivative. If we evaluate this at pi over 2, it's positive. So pi over 2 is a relative minimum. If we evaluate this at 3 times pi over 2, it's also positive. So we have relative minima at x equals pi over 2 and x equals 3 pi over 2. And if we evaluate the second derivative at the two other critical points in this interval, which are pi over 6 and 5 pi over 6, they're both negative. So we have relative maxima at pi over 6 and 5 times pi over 6. What about where the curve is concave up and concave down? So if we want to know where the curve is concave up, we want to find where the second derivative is positive and we get a lot of intervals, none of which are in a form I like, and you can't use f-solve with an inequality. You only can use solve. So what can we do? We can see here's concave down, concave up, concave down, concave up again. So this function is going to have 1, 2, 3, at least, maybe 4 inflection points in this interval. So how do we find where the second derivative is equal to 0? That's maybe, and I get all these numbers, which I can't understand because they're not. Let's try f-solve. Now, let's see if we can solve this for x going from 0 to 2 times pi. So we're only given one, but we know there are more. One, that's probably right about there. So suppose we want to know if there's one somewhere in this region. This is somewhere around 9/4. Let's try between 2 and 3. Excellent. So 1, 2, it's going to be someone around there. Maybe we'll try between 3 and 4. Mm-hmm. 3.7, a little bit more than pi, somewhere around there. Then so it's going concave down, inflection point, concave up, inflection point, concave down, inflection point, concave up. And it might even be turning from concave up to concave down somewhere in here. So let's look for that. That maybe is between, let's look between 5 and 7. See what happens. Let's try this maybe between 5 and 2 times pi. Let's see if that works. Aha, we got one. So we found 4 points where the second derivative is 0. So these are inflection points. The above 4 points are inflection points. And studying the graph, we can see where the curve at the inflection point is changing from concave down to concave up. That's what's happening here, down to up, and then up to down, and then down to up, and then up to down. Yeah. If I extended this a little bit, you can see here it's concave up, and then it really does change to concave down, and it's just somewhere before 2 pi. It's a very interesting curve, but we're just looking at it from 0 to 2 pi. If you look at it on the whole real line, since this is periodic, it repeats every 2 pi, you would get infinitely many inflection points. Let's go to part 2, problem 2. Maybe problem 2a. So we have this function f, x goes to 4 times x plus 3 . Four times x plus 3 divided by 2x minus 1. And the horizontal asymptotes, you take the limit as x goes to plus or minus infinity. So the limit of f of x as x goes to infinity well, I wrote it with a capital L, so that just states the problem. Say equals, and I write limit lowercase, I get 2. And if I want to go to minus infinity, it's also 2. So this function has a horizontal asymptote, the line y equals 2. And this function is undefined where the denominator is 0. If we solve 2 times x minus 1 equals 0, we get a half. So we have a vertical asymptote at x equals a half. I'll just write it as 0.5. And you can see all this clearly if you plot f of x. Here's your vertical asymptote. Now, you can't really see what's going on horizontally. So suppose I go out further. Let's say, and I mentioned, so maybe I'll go from x equals minus 3 to 3, and y equals minus 20 to 20. Let's see what the graph looks like. And suppose along with this, I plot just the horizontal function, the constant function, y equals 2. So this is going to be, this is the horizontal asymptote. If I go actually off to 200, that's pretty far. Yeah. Sorry. I wanted to change the x and not the y. So maybe x goes from minus 10 to 10. There, you can see, here's the vertical asymptote at x equal to a half. And here's the horizontal asymptote. And if I go further, if I go out to 100, and you can't even tell the difference between this horizontal asymptote and the function. They're so close together. Let's do another one. Suppose we do problem 2b. So here my function f is x goes to 5 minus 2 times x to the power 3/2 divided by 3 times x squared minus 4. Oops, yeah, okay. What does it look like? Plot f of x. So it looks like there's a vertical asymptote here. And is there a horizontal asymptote? X goes to minus 10 to 10. Well. So this is interesting because if you look at this carefully, x to the 3/2, that's the square root of x cubed. Square root is only defined for a positive number. So this is only defined for x positive or 0. So that's why the graph really starts at 0. Now, there's a vertical asymptote where the denominator is 0. So if we solve 3 times x squared minus 4 equals 0 for x, we get 2 solutions, only one of which is positive. And if we look for a positive solution, it's this number. If we wanted it algebraically, oops, it doesn't like that. Interesting. So if we do F solve, yeah. So we have a vertical asymptote at x equals 1.1547 ... If we just wanted to solve this equation, let's see. We know what the answer is. Yeah. The positive solution is 2√3/3, which is the same as this. If I put in greater than 0, it doesn't like that. I don't know why. But if we just say solve, it gives us the 2 roots where this is the positive root. So that's where we have a vertical asymptote. And to find a horizontal asymptote, we take the limit as x goes to plus infinity, and this function is going to 0. So we have a horizontal asymptote at x equals 0. If we go out further, you can see that a little bit more clearly. Suppose we go out to 100. Yeah, thing is going up, it's approaching 0. Go out to 1,000. Yeah, getting close. Okay, so that's some of the problems, and I'm happy to do more. If you have questions, you can ask me either by an email to do some more problems or at one of the Zoom sessions.